Let us have a look at a couple of examples on how to define a CDF of a discrete random variable. Let us start with an example or question that we looked at before. Remember question 13 on exercises using the PMF or exercises on the PMF. So in that video, we looked at question 13, which is based on a computer business that has 6 telephone lines, and where random variable x was defined as the number of lines in use at a specified time. So suppose that the PMF, we assume that it's a valid PMF. So suppose that the valid PMF of a random variable x is given in the table below. All right, so we have possible values 0, 1, 2, 3, 4, 5, 6, and we have the direct probabilities here of observing 0, observing 1, 2, 3, 4, 5, and 6. All right, so how can we then define our CDF of a random variable x using a table? Okay, so if you're going to define it using a table, we start with drawing a table where the first column is the possible values for our random variable x, denoted by small letter x. And so we have here possible values 0, 1, 2, 3, 4, 5, and 6. Okay? And we have here probabilities P0 is equal to the probability that x is equal to 0. That is equal to 0.1. P1 is equal to 0.15. P2 is equal to 0.2. P3 is equal to 0.25. P4, 0.2. P5, 0.06. And P6 equal to 0.04. All right, so now if x calculates for us the probability that we would have observed at most that particular possible value, right? So here we have f0, which calculates the probability that x is at most 0. So now, since 0 is the smallest possible value for our random variable x, we do not have any other values that are less than 0, right? So we'll opt for probability that x is equal to 0, which is equal to 0.1. Okay, now f1 is a probability that x is at most 1. Now, which values of x are less than or equal to 1? It's 0 and 1 itself, right? So this is equal to 0.1 plus 0.15. That is 0.25. Now, f2 is the probability that x is at most 2. Which values of x are less than or equal to 2? It's x equal to 0, 1, and 2. So now we're adding up the probabilities for x equal to 0, 1, and 2. And that is equal to 0.1 plus 0.15 plus 0.2. And that probability is 0.45. Now f3 is equal to probability that x is at most 3. And that is equal to the summation of 0.1 plus 0.15 and 0.2 and 0.25. And so that probability is 0.7. F4 is the probability that x is at most 4, and that is equal to 0.9. F5 is the probability that x is at most 5. So which values of x are less than or equal to 5? It's x, 0, 1, 2, 3, 4, and 5. So now that probability will add up to 0.96. And then if 6 is equal to the probability that x is less than equal to 6, so at most 6, and that is just equal to the sum of all probabilities here, it will add up to 1. Okay, cool. So now we have the CDF in tabular form or in a table form. Now we can define the CDF as a formula. So how do we define it as a formula? Knowing the possible values of a random variable x and the PMF, as well as the respective fx values. All right, so as a formula, we will firstly write down here capital Fx. This is probability that x is less than equal to some particular possible value of x, possible value x. so fx is equal to, and we will use large curly brackets, all right? And we will start with the smallest possible value for our probability, which is 0. So we'll say that if we have any x value that is less than the smallest possible value in our example, in this case it's 0. This is the smallest possible value for exercise 13. And so if I have any x value that's less than this possible value here, it will have a probability of 0, right? So remember, we're accumulating, we're adding on, right? So then the next interval that we will look at, since we're adding from one to the next, it will be the interval where x is greater equal to 0, including 0, but excluding the next possible value of 1. So now what is that probability there? That probability of f x value is equal to 0.1, right? Then we're adding on, so accumulating to the next possible value, so greater equal to 1, but less than the next point, which is 2, and that accumulated probability is equal to 0.25. And then for any possible value that is from 2 onwards, but excluding the next possible value of 3, the accumulated probability there is equal to 0.45. And for x greater equal to 3 but less than 4, the accumulated probability there is equal to 0.7. And for x greater equal to 4, less than the next point, which is 5, the probability there is equal to 0.9. And for any x, or any x value that you're looking at from 5 onwards, greater equal to 5, including 5, but less than the next point, the accumulated probability there is 0.96. And for x greater equal to 6, the accumulated probability there is 1. So this fx function, it's a formula that tells us the probability of having at most that specific value. So the probability that x, let's say probability that x is at most equal to 0, we look and see where x includes 0, it's this interval here, that probability is 0.1. The probability that x is less than equal to 1, which includes 1, right? Where is 1 included? It's in this interval here. That probability is 0.25. The probability that x is less than equal to 2, where 2 is included in this interval, that probability is 0.45. Now, what is the probability that x is at most 3? Where 3 is included, the accumulated probability is 0.7. And the probability that x is at most 5, where 5 is included, that probability is 0.96. Now, if we're given intervals, then we can calculate the probability or cumulative probability of any possible value, right? So let's say we're looking at possible value 2.5. So what is the probability that x is less than or equal to 2.5? So if you think about it, every time we calculate these types of probabilities, think of the possible values of x that are less than or equal to 2.5. So in your mind, think about them or write them down for yourself. So it's possible value 0, 1, and 2. We don't have possible value 2.5. But we see that, yes, there are other possible values that are less than 2.5, which is 0, 1, and 2. And so this means that this probability is just equal to probability of x less than equal to 2. And that is equal to f of 2. and that is equal to, where is 2 included? It's right there. It's 0.45. All right. Does it make sense? Okay, cool. We will do couple of other examples. But this is how you define it as a formula. So you have capital Fx equal to, and then curly bracket, minimum value there always starts with 0, always ends with 1. So it's 0 for any value that's less than your smallest possible value. In this case, we have less than 0 there because in the exercise, or exercise 13, the smallest possible value was 0. So if the smallest possible value was 1, then we would have had x less than 1 there. Okay? So we'll look at other examples so that you completely understand. All right, so how do we then define the CDF using a step function or a graph? So we know from our formula, this is how the CDF looks like. So we have probability of 0 when we have any x less than 0, probability of 0.1 for any x that includes 0 less than 1, greater or equal to 1 less than 2, greater or equal to 2 less than 3, greater or equal to 3 less than 4, greater or equal to 4 less than 5, x greater or equal to 5 less than 6, and then greater or equal to 6. Okay, so the probabilities are given as 0.1, 0.25, 0.45, 0.7, 0.9, 0.96, and finally maximum probability of 1. Alright, so we can use the formula to actually help us draw the step function. Okay, and before you draw your graph, obviously you need a title, right? So you can give your graph a title, CDF x of random variable x, where random variable x denotes the number of telephone lines that are in use at a specific time or hour. Alright, so we have here, you draw your graph, start drawing your axes. On the y-axis, you have f(x), and on the x-axis, you have possible values of a random variable x. So of possible values 0, 1, 2, 3, 4, 5, and 6. And so how are we going to then draw the step function? So we will use the formula. The formula will guide us. So the formula says, if we look at the first possible values there, for any x that is less than 0, f(x) is equal to 0. Okay, so we will draw a line. Any x value that is less than 0, so the negative values or anything on the left hand side of 0, f(x) will be equal to 0. Okay, so we'll draw an arrow like that. Anything less than 0. We have here a probability value of 0. Okay, then the next interval here. So for x between 0 and 1, including 0 but not and excluding 1, f(x) is equal to 0.1. So let's say 0.1, it's somewhere there. So we will draw from between 0 and 1, including 0 and excluding 1. So we will color in the circle or this dot to indicate that we're including the possible value of 0. Okay, so for some textbooks, they use a closed circle, a point, and then an open circle there. So we could use an open circle there, or we could just have a line. All right, so we have here between for x between 0 and 1, f(x) is 0.1. Okay, then the next interval for x between 1 and 2, including 1, excluding 2, f(x) is 0.2. Sorry, it's 0.25. Okay, so we can go there between 1 and 2, including 1, excluding 0, the probability there if x is equal to 0.25. The next one, we have interval x greater equal to 2 less than 3 if x is equal to 4.5. So we'll say 4.5, it's somewhere there between, includes 2, excluding 3. We have a probability of 0.45. Okay, and then the next interval, x between 3 and 4, probability, or if x is equal to 0.7. So we'll go there by 3, including 3, excluding 4, probability there is 0.7. The next interval between 4 and 5, the probability is 0.9. Okay, and then the last this interval here between 5 and 6, probability is 0.96. And then the last interval here, x greater equal to 6 onwards. 6 onwards, right? X greater equal to 6 onwards. We have here maximum probability of 1. What does it mean? So it means that if I ask you to calculate probability of x is at most 8, since 8 is greater than 6, f x or f of 8 is automatically equal to 1 just by looking at the formula or looking at the step function. If 8 is here, then the corresponding fx value, it's 1. All right, so it's 1 for all x greater equal to 6, right? Since x less than equal to 8, if we look at the possible values of x that are less than or equal to 8, its possible values 0, 1, 2, 3, 4, 5, and 6. We don't have possible values 7 and 8. It starts from 0 and ends at 6. These are the possible values in this exercise. And so that will be equal to P0 plus P1 plus P2 plus until P6. And if we add up all the probabilities, it should give you a probability of 1. All right. So in the step function, I could ask you, for example, to calculate or give the probability that probability that x is at most. Let's say, what's the probability that x is at most 1.8? All right, so in your mind, you can think of all the possible values of a random variable that is less than or equal to 1.8. So we know that we have possible values only 0 and 1. If we have the PMF, we can just calculate it as P0 plus P1. All right, we should get to the same answer. Whether using PMF or CDF, it should lead to the same answer. All right, so in using a formula, we will look at, okay, so 1.8, where is 1.8, or in which interval do we have 1.8 in our formula? So if you look carefully, so 1.8 is in this interval here, right? Okay, so any x that's between 1 and 2, including 1 but excluding 2, will have the fx value for that particular possible value at 0.25. So probability that x is less than or equal to 1.8 is equal to 0.25 using the formula. Now if you think about it, and you use the PMF, we will have here possible values of x that are less than or equal to 1.8. It's x equal to 0 and 1. So the probability will be 0.1 plus 0.15. That is 0.25. Is it exactly the same answer as in the formula? Yes. All right, so the different ways of getting to the same answer as long as you get to the answer. All right, so allow yourself to be creative. If maybe you cannot see it using the formula or the step function, you can think of the PMF. So if you have the CDF, it means that you automatically have the PMF. If you have the PMF, you automatically have the CDF, all right, because they all have a relationship. Okay, so another thing that I want you to take a look at is that these points here, if I give you a step function only, or if you have a step function only of your CDF, then you can get the possible values of your random variable by looking at the points that are included, right? So you see that on the graph, x equal to 0 is included because you have a colored in a closed point there, circle. And then x equal to 1, that's also possible value. X equal to 2, possible value. X equal to 3, x equal to 4, x equal to 5, and x equal to 6. That's also possible value, all right? And also, we can get the exact probabilities or the PMF from the step function as well. How can we do that? All right, so the probabilities that x is equal to 0 or x equal to 1 or x equal to 2, x equal to 3, it's given by the jumps in between the steps. So the probability that x is equal to 0, it's given by the difference between 0.1 and 0 there. So it is the difference or the jump there, the difference between that jump. So probability that x is equal to 0, it's given by the difference there, which is 0.1 minus 0, that is 0.1. The probability that x is equal to 2, it's given by that jump there, that space there. So this space here gives us probability that x is equal to 2. And that is equal to 0.45 minus 0.25, right? 0.45 minus 0.25, that is equal to 0.2. The probability that, if we look here, this one is, 4. The probability that x is equal to 4 is given by that jump here. That is equal to 0.9 minus 0.7, equal to 0.2. Now if we go to a table, we see that px is equal to 0.2 when x is equal to 4. Do you see? Alright, so now this one corresponds to what? X equal to 6, okay? So probability that x is equal to 6, it's given by the space right there. That is 0.96 minus 0.9. That is 0.06. Make sense? Alright, I hope it makes sense. So from the step function, first it's called a step function because of these jumps or the steps, right? So we have a disjoint steps because x could either be 0 or 1 or 2 or 3 or 4, 5 or 6. All right, it's not a continuous random variable, it's a discrete random variable. And from the step function, we can get the cumulative distribution function. We can get the possible values of our random variable. We can also get the PMF. So we can get this whole entire table from just looking at the step function. So you should be able to do that from just this graphical illustration here. All right. Okay, so at the end for this example of exercise 13, your step function will look like that, where for any x less than 0, we have a probability of 0, and for any x that's greater than 6, that probability there, at most 7, or at most 8, or at most 9, or at most 10, it will, for all of those possible values there, f of those values will be equal to 1. Alright, so we see that also from the step function, we see that our CDF is a non-decreasing function. It's actually increasing, and it will asymptotically converge to probability of 1. Alright, make sense? Good. In this example, we will be deriving a CDF function of a random variable when given a specific PMF function, all right? So this example is based on exercise 84 on page 145, or else it's related to examples 2.4 and 2.7, which you did in chapter 2. So this example says, suppose that individuals that are treated with a drug either have an adverse reaction, an allergic reaction, or not. So a medical researcher will administer the drug to one individual after another until the first allergic or adverse reaction occurs. So you have to continue the experiment until you get an A. If you do not get an A, then the experiment must continue, right? So all outcomes at the end must end with the event where we have an allergic reaction, right? Then additional information says 20% of individuals experience an adverse or allergic reaction to this certain drug. So let us list the possible outcomes. All right, so it might be that the first patient that we give the drug to might have an allergic reaction to it. So we might have only gone through one patient and immediately they got an allergic reaction. Or it might be that the first patient did not get an allergic reaction, and so we continued giving this drug to other people. And so maybe the first patient did not get an allergic reaction, but the second one did, right? Or the first one and the second patient did not get an allergic reaction, but the third one did. Or it might be that we gave the drug to 3 people, they were fine, but only the 4th person got an allergic reaction. Or maybe we gave the drug to 5 people, right? Where 4 of them were fine and only the 5th got an allergic reaction, and so on. So we see that we have an infinite number of possibilities or number of outcomes in this example. So now the probability of getting an adverse reaction, where it's from once we give it to one patient, let's say the first patient gets an allergic reaction, then the probability that one individual will get an allergic reaction is equal to 0.2, right? And the probability that one individual will not get an allergic reaction, it is 0.8. So either they get an allergic reaction or not, right? Now the probability that the first patient does not get an allergic reaction but the second one did, it's equal to 0.8 times 0.2. Okay, we assume that the individuals are independent of each other. So if a drug is given to you as well as your sibling, we assume that you might have different reactions, right? Even if you're related. Or if a drug is given to you and your friend, we will assume that there's a possibility of having different reactions. And so what happens or how you react should not influence how somebody else reacts to the drug. All right? Now the probability that 2 patients did not have an allergic reaction, but only the third one got an allergic reaction, is equal to 0.8 times 0.8 times 0.2. All right? The probability then that 3 did not get an allergic reaction, but only the 4th one got an allergic reaction, that probability is 0.8 to the power 3 times 0.2, right? And the probability that 4 did not get an allergic reaction, but only the 5th one got, that is equal to 0.8 to the power 4 times 0.2, and so on. Do you see the pattern? There's a pattern here, right? So if, for example, I say 10 patients were given this drug, and from the 10, or we did the experiment until we got one or the first allergic reaction, right? So it means that if the drug was given to 10 patients, and for those 10 we got one allergic reaction, then it means that 9 did not get an allergic reaction, and then the 10th one did, right? Because we'll continue the experiment until we get an allergic reaction. The moment we get an allergic reaction, we stop the experiment. So these are the possible outcomes. You can stop the experiment for the first patient, or after the second patient, or third patient, and so on. So we see that there is a pattern here. And so the probability, or PMF function, can be given as 1 minus p to the power x minus 1. So if 10 patients, or we did the trial 10 times for 10 patients, then 9 of them did not get an allergic reaction, and the 10th one did, right? So a PMF function is given as 1 minus p to the power x minus 1 times p, where p is the probability of getting an allergic reaction. 1 minus p is the probability of not having an allergic reaction. And so this PMF is defined for x equal to 1, 2, 3, 4, 5, and so on. And the probability is 0 otherwise. So for any x value that's not greater or equal to 1, or for any x value that's less than 1, the probability there is equal to 0. Meaning if x is equal to negative 2, probability that x is equal to negative 2 is 0. Doesn't even make sense, right? So we're counting here the number of patients that, or trials, the number of times we would have given this drug until we get an allergic reaction. Okay, so let us say that is the PMF. Now how do we derive the CDF from this PMF? So we will start with the definition. Always start with the definition, okay? It says that if x is equal to the probability that x is at most some particular value, right? Okay. So now, this probability that x is at most some possible value is also equal to the sum of the individual probabilities, right? When y is at most, that's a possible value. Okay, and now this is also equal to, so we're summing all the possible probabilities, which is 1 minus p to the power y minus 1 times p, when y starts from 1 to x, all right, to some x, because a function of x. Reason why I'm using y here is that mathematically it would not be correct to write here x equal to 1, you summing up until x, and you have x minus 1. No. So this x, remember this is if x is a function of x, x can take on any possible value from 1 onwards. And so we need to get a general formula that gives us the probability of observing at most x, right? And we know that x goes from, or the minimum value, it's 1, and to some maximum large value. It could go up until infinity, all right? So for any x here, the function or probability that x is at most x, we will use here random variable, we will use here y, the letter y, instead of putting in the letter x in the formula, all right? Okay, so this is equal to, if y is equal to 1, it's 1 minus p times 1 minus 1 times p plus 1 minus p to the power 2 minus 1 times p plus 1 minus p to the power 3 minus 1 times p plus. Okay? So you're adding and adding and adding, since x can go up until some infinite number, right? So we will be adding until, since we are summing until x, so y must be at most x, then we're summing until x. We have here the formula is x minus 1 times p, all right? So y equal to 1, 2, 3 until x. So we have there x minus 1 here. Okay? Now this is equal to 1 minus p to the power 0 times p plus 1 minus p to the power 1 times p plus 1 minus p to the power 2 times p plus until at most x. The formula will say it's this function here, or expression, this function will be 1 minus p to the power x minus 1 times p. Okay, so now how do we write this as a formula? We see that it is equal to p, right? The common denominator here is p, and p, times the sum. So we can take out the common multiple, put it outside or in front of the summation sign, times the sum of 1 minus p to the power y, where y starts from 0, okay, to x minus 1. Make sense? Summing to x minus 1. So it's p times 1 minus p to the power 0 plus p times 1 minus p to the power 1 plus p times 1 minus p to the power 2 plus until p times 1 minus p to the power x1. So we can take out the common multiple and then multiply it by all of these, add up all of the other items or expression in your summation sign. And so this whole summation times p is summarized by this expression here. Okay? But we're not done. So we can actually get a final formula or function of our CDF. So mathematically, there is an expression that says the summation of a to the power y, where y goes from 0 to k, is equal to 1 minus a to the power k plus 1 divided by 1 minus a. So it's the sum of a to the power y, where y goes from 0 to k, that is equal to 1 minus a to the power k plus 1 divided by 1 minus a. So now what do we have here that looks similar to this expression here? So we have a summation sign. So summing 1 minus p to the power y, where y goes from 0 to x minus 1. So in this case, we see that yes, we have a y there similar to this expression. We have y equal to 0 similar to that expression there. But we have, instead of a, we have a 1 minus p, right? And instead of a k, we have a x minus 1. So in this case, we could say that this expression here is equal to 1 minus, we said a is 1 minus p, right? Okay. Now our k is x minus 1, so x minus 1 plus 1. There, that's the power of 1 minus p. And then the denominator, we have 1 minus p. And so this is equal to 1 minus p to the power x, all divided by p, right? 1 minus 1 plus p. So the denominator there will be p. So this means that f of x is equal to p times 1 minus p to the power x divided by p. And so that p and the denominator p, that cancels out. And so it's 1 minus p to the power x. And so as a formula, we will say that fx is equal to 0, firstly, 0 for any x that's less than 1. Why 1? Because the minimum value for our random variable x is 1. And so possible values for our random variable x is 1, 2, 3, 4, 5, up until some infinite number. So for any x value less than 1, we have an fx equal to 0. And for any x from 1 onwards, we have here a probability function of 1 minus 1 minus p to the power x. Alright? And this x here, so it's any x greater or equal to 1. So, for example, the probability that we would have given the drug to at most 3 patients, where the third one got an allergic reaction, is equal to 1 minus 1 minus p to the power 3. If then we're looking at 10 patients, then probability that x is less than or equal to 10, then the probability is equivalent to 1 minus 1 minus p to the power 10. Make sense? Good. So now if we draw the CDF using a step function, then it will look like that, where we see that our CDF is a non-decreasing function, it's increasing, and it will converge up until probability of 1. Since fx, those are one of the properties, greater or equal to 0, less than or equal to 1. Alright, cool. So that is one of the examples in your textbook. In this third example, we will look at exercise 22. So exercise 22 says, a consumer organization that evaluates new automobiles customarily reports the number of major defects in each car examined. So let x, random variable x, denote the number of major defects in a randomly selected car of a certain type. So x denotes the number of major defects, and we have a CDF of random variable x given below, and we see that our CDF is defined using a formula. So it's in a formula form, since we have fx equal to, and we see the curly brackets and the different probability values for different intervals or possible values of random variable x. Alright, so before we even continue or answer the questions, let us look at the possible values of x. So what are the possible values of random variable x? Possible values of random variable x, what are the possible values given the CDF? Do you know? What's the first one? It is 0, right? Okay, so we will look and see which intervals includes some possible values. So we see that these intervals include some specific values. And so we will say that the possible values of a random variable x, it is 0, 1, 2, 3, 4, 5, and 6. Those are possible values for our random variable x. Alright, so now let us define the PMF. Alright, in tabular form, so use a table. Alright, so if we draw a table, the first column should be a possible values of our random variable x, which is 0, 1, 2, 3, 4, 5, and 6. Do we know how we got those possible values? Yes, right? So we look and see for all of those intervals where that possible value is included. So x could be greater or equal to. X could be greater or equal to 1, or equal to 2, or equal to 3, or equal to 4, or equal to 5, or equal to 6, right? So that's how we take note of the possible values for our random variable x. Alright, so if you look carefully at how it is written, this is how you need to write your CDF(fx) as a formula. So we have the greater than sign, greater than or equal to sign on the left hand side, then less than, greater equal to, then less than, greater equal to some specific value, then less than, greater equal to some possible value, then less than, greater equal to some possible value, then less than, and so on. Alright, so our PMF, how can we then define our PMF? So we have first column, possible values of our random variable x. Second column, it's the probability. So remember, px gives us the probability that x is equal to some specific value. Alright, so using our CDF, can we get our PMF? Yes, we can. So the probability that x is equal to 0, P0, is equal to the difference between these two. So it's 0.06 minus 0, which is equal to 0.06. So the probability that x is equal to 0 is equal to 0.06. The probability that x is equal to 1 is equal to the difference between these two. So the jump there, it's 0.919 minus 0.06. That is equal to 0.13, right? Then the probability that x is equal to 2, it's the jump there. So it's 0.39 minus 0.19. That probability there is equal to 0.2. P3 is the probability that x is equal to 3. So looking at that interval there, and it's the jump there. So it's the difference between 0.67 and 0.39. So that is equal to 0.28. P4, probability that x is equal to 4. So that interval there, it's the difference between that jump there, 0.92 minus 0.67. That is equal to 0.25. And then P5 is equal to the jump between those two there, 0.97 minus 0.92, which is equal to 0.05. And then lastly, P6, 6 is there. P6 is equal to the difference between those two there. It's equal to 1 minus 0.97. That is equal to 0.03. So at the end, we have PMF defined for values 0, 1, 2, 3, 4, 5, and 6. And the probability that x is equal to 0 is 0.06. Probability that x is equal to 1 is 0.13. X equal to 2, 0.2. X equal to 3, 0.28. X equal to 4, 0.25. X equal to 5, 0.05. And x equal to 6, 0.03. Now we see that all the probabilities are positive. Yes, 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 yes. Now if we add all the probabilities, it should give you a total probability of 1. Okay, so we have now defined a valid PMF. Good. Now we can continue and answer the rest of the questions. So in a test or exam, I do not want to train you for a test or exam. This is general things that you need to look out for. But if you're given a CDF and you're not given possible values for random variable x, then it is the first step that you take is to have a look and see what the possible values for random variable x is. And then you can, from then onwards, if you do have time, draw for yourself the PMF in tabular form. All right, just so that you can see if your answers match if you use the PMF as well as if you use the CDF. All right, now the first question says calculate the probability that x is equal to 2. So we're calculating here P2. All right, using directly from the CDF. Okay, so if you calculating it directly from the CDF, then this probability that x is equal to 2 is equal to the probability that x is at most 2 minus the probability that x is at most 1. All right? So directly using the CDF, that's instruction, then you need to write down in terms of the notation for the CDF. So it's equal to f of 2 minus f of 1. That is equal to 0.39 minus 0.19. And that probability there is 0.2. Now, you can verify and look and see what you wrote on the side. And yes, it corresponds to the PMF. Okay, then B. Calculate the probability that x is greater than 3. All right, so x greater than 3, meaning we're looking at possible values, 4, 5, and 6, right? And we're excluding 0, 1, 2, and 3. Isn't that correct? So any possible value that's greater than 3, here we have possible values 4, 5, and 6 only. Those are the only x values that are greater than 3. And so we will say, notation-wise, using a CDF, probability of x greater than 3 is equal to 1 minus probability that x is less than equal to 3. So excluding everything that's less than 3. All right? So in general, probability that x is greater than b is equal to 1 minus the probability of x is less than equal to b. Okay? So in this case, it's 1 minus f of 3. That is 1 minus, where is f of 3? So where's 3 included in your CDF? 3 is included there, that row there. So f3 must be 0.67. 1 minus 0.67, that is equal to 0.33. So to verify for yourself, you could say it's P4 plus P5 plus P6, that is equal to 0.25 plus 0.05, which is 0.3, plus 0.03, which is 0.33. Are these answers the same? Yes, they are. Cool. And now C. For C, it says calculate the probability that x is greater equal to 2 and less than equal to 5. So in your mind, you will think of the possible values of x that fit this criteria here, right? So it means that it's x is equal to 2, 3, 4, and 5, right? All right. Now, using CDF notation, we know from our proposition that says probability that x is greater equal to a less than equal to b is equal to f of b minus f of a minus, or if we have integers, meaning for the specific scenario we have 1, 2, 3, 4, 5, 6, 7. We know that that is equal to, then the probability of x greater equal to a less than equal to b is equal to f b minus f of a minus 1. So remember this f minus here, it is the next or the lowest value, or the value that is on the left hand side of a. Alright, so a minus is the value on the left hand side of a. In this case, if we have here possible values 0, 1, 2, 3, 4, 5, and 6, a minus will be the next, so the lowest value on the left of a. If a is equal to 2, so a is 2, b is 5, then a minus is 1, right? Or since we have here the specific integers where we have possible values a plus 1, a plus 2, blah, 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 until b, or until b plus 1, then a minus 1 will be 2 minus 1, which is equal to 1. All right, so going back let's go back to calculating this if you're confused. The probability of x being greater or equal to 2, less than or equal to 5, using the proposition, is equal to, if b is 5 and a is 2, then it's equal to probability of x being less than or equal to 5 minus probability of x being less than or equal to the value on the left hand side of 2, which is 1. So that is equal to the probability, or in other words, I can write it as probability of x less than or equal to 5 minus probability of x less than 2. So you're excluding 2. Remember here you're including it. So it's equal to f of 5 minus f of 1. In this case, it's equal to, so f of 5, where is it? Where is 5 included? It's in this interval here. So f of 5 is 0.97. Where is 1 included? F of 1. F1. So 1 is included in this row here. So F1 is 0.19. So f of 5 is 0.97 minus 0.19. Alright? So then that should be equal to 0.78. Cool. 0.78. Awesome. And then D, calculate probability of x being greater than 2 and less than 5. D, probability of x greater than 2, less than 5. Which values of x are between 2 and 5? So excluding 2 and excluding 5. So it's 3 and 4, right? So if you want to verify your answer, you will know that you can just add P3 and P4. All right, so now, what is this equal to? This is equal to the probability that x is greater or equal to 3, less than or equal to 4. All right, and now this is equal to, if this is A and that is B, then the proposition says it's equal to probability that x is less than or equal to 4 minus probability that x is less than 3, which is equal to probability of x less than or equal to 4 minus probability of x less than or equal to 3 minus, or A minus in this case, which value is on the left hand side of 3? It is 2. All right, so it's equal to f of 4 minus f of 2. F of 4, we go to our CDF formula. Let us look and see, where is 4 included? 4, 4, 4, 4, 4, there. All right, so F4 is 0.92. And F of 2, where is 2 included? In this row here, F of 2, 0.39. So f of 4 is equal to 0.92 minus 0.39. That is equal to 0.53. Now, if you want to verify and see if you did it correctly, we can also use the PMF, right? So probability of x greater than 2, less than 5, is exactly the same as P3 plus P4. And that is equal to, what is P3? It's equal to 0.28. What is P4? Is equal to 0.25. 0.28 plus 0.25 equal to 0.53. We have exactly the same answer. Cool, happiness. So now, in a test, the instruction would say directly from the CDF, meaning you must use the CDF. So you must use the notation f of x, f of 1. Do not just write P3 plus P4 without using the CDF. So you have to use the CDF. Use F4, use F2, and then you can verify. If you're in a situation where you really do know, you cannot see anything, you don't know how to use the CDF, before the semester test, I hope you get to a point where you know how to use the CDF to calculate probability. But you can then verify using your PMF, and you know what the value should be. So if you know what the final answer should be, then you can work your way backwards in a way, or use the CDF to get to that answer. But I'll be expecting you to use this notation. Do not just write P3 plus P4. I know at the end the answer will be correct and will be the same, but the instruction would be use the CDF to calculate the probability. Okay? Okay, so at the end of section 3.2, we have managed to use a couple of tools. So I would suggest that you start creating a toolbox for yourself, since for the semester test and for the exam, it will be a closed book test written on campus. And so it would be wise for you to make a note of all the formulas or the important things that you need to look out for in chapter 3. So in chapter 3, you should know the definition of a PMF. What does the PMF stand for? What are the criteria or those 2 points that make a PMF valid? You should know what CDF stands for. You should know the properties. You should know the definition. And you should be able to calculate probability, represent or define the PMF and CDF using a table, formula, or via some graphical illustration. All right, so that's it. Cool.